In this example, we have a mechanism which is made up of links OB and AB. What we know is that OB is pinned to ground at O. AB has end A moving along a straight vertical line, and we know at this instant in time we know its speed, and we know that it's slowing down at a rate of 0.1 meters per second squared. Then links O, B, and AB are pinned together there at B, and at this instant when theta is 90 degrees, what we want to do is find the angular velocity and angular acceleration of each of the links AB and OB. So what I've done is I've drawn the mechanism in the position of interest to us here when AB is basically horizontal and OAB make a right triangle. I'm representing the length of OB by L and AB by D just so I don't have to put in numbers until the end. But the idea here is that we're looking for both velocity and acceleration analysis of this mechanism. So for each one of those, we have to write down a velocity equation for each link for the velocity part. For the acceleration part of the analysis, we'll write an acceleration equation for each link. So anticipate that as we go. So we'll begin with velocity because we need to have that first before we can tackle the acceleration. So for velocity, I'm going to begin with link OB. I have x and y defined as here. Write down the velocity of B in terms of velocity of O plus omega OB crossed with the vector which goes from O to B. O is a pin. It's pinned to ground, so that's a 0. Omega OB, we don't know that. That's one of the things we're asked to find. So I will write it down because I know it's going to be rotating about the k-axis. I don't know its magnitude and don't really know whether it's positive or negative. I assume plus. Let math tell me if I'm wrong here. Then going from O to B. What I will do is, let's say, write down this angle there, phi, where phi is going to be, the sine of phi is going to be d, the known length there of d divided by the length there of L. So phi should be considered to be a known at this point. So in going from O to B, in x, what I need to do is write that down as d. In y, I'm going to be going as minus L cosine phi. So when I do the omega cross r, k cross j is a minus I, so this becomes a plus L omega OB cosine phi in the I. In the j, I've got a d omega OB in the j. So that's for link OB. For link AB, I'll do the same thing, except here I will relate the velocity of B back to the known velocity of A. We know A is moving in the y direction, so it's VAJ. We know VA. Omega AB we don't know. I'm going to assume it's plus K and let math tell me if I'm right or not. And going from A to B, that's a positive DI. So in the end, when I cross through and combine terms, I get VA plus D omega AB in the J. Okay, so what I have are two vector expressions. VB for link OB, vector expression for VB using link AB. They've got to be the same thing. So if I equate these and then balance out my coefficients for I and j, let me do I first. If I balance out I, there's an L omega OB cosine phi from the first equation. The second equation, there is no I component. So it says right away that we know the angular velocity of length OB is a 0. J component. J component says that I have, from the first equation, you get d omega OB is balanced out with VA plus d omega AB from the second equation. I just saw that omega OB is a 0. So from this equation, I get that omega AB, the angular velocity of length AB, is a minus VA over D. Okay, so the negative sign here, first I should say that VA is a plus 0.4. So in the end, my omega AB is going to be a negative number, and since it's a negative, it means that up here, when I originally wrote down the omega vector, I assumed plus. The negative sign meant I was wrong. So being as I guessed counterclockwise and it's wrong, that means it's in the clockwise sense. So I've got omega OB and omega AB. Repeat the same process for acceleration. Write down an acceleration equation for each link. So OB, I will say the acceleration of B is equal to the acceleration of O plus alpha OB crossed with the vector which goes from O to B minus omega OB squared RB with respect to O. Well, O is a pin to ground, so that velocity is a 0. We just saw that omega OB is a 0. So alpha OB, don't know what it is, but I'm going to assume it's in the positive K. Let math tell me right or wrong. From O to B is a DI and a minus L cosine phi in the J. When I carry through the alpha cross R, I get a plus L alpha OB cosine phi in the X. In the J, I get a D alpha OB in the J. So that's what we get from link OB. Repeat the same thing for link AB. Link AB, I'm going to write acceleration of B in terms of the acceleration of A, which we know. Acceleration of A, we know what that is. I'm just going to write it as J. I'll put the number and the sign of that number in just a bit. Alpha AB, unknown. So I will write it as a plus. Let the math tell me whether that's right or not. From A to B is a DI minus omega AB squared DI, like this. I cross alpha with R, I combine my terms, and I get a minus D omega AB squared in I. In J, I get A sub A plus D alpha AB K cross I gives a J. I have two expressions for the same thing, the acceleration of B. Components must be the same, so when I equate these, If I balance out, what do I want to do? Probably no advantage one way or the other. Well, let me try I first. Let me try the I components. L alpha OB cosine phi is equal to minus D alpha AB squared. So this says that the angular acceleration of OB is going to be a minus D omega AB squared. We know that. Divided by L cosine phi. So the negative sign means my original assumption of plus was wrong, but plus meant counterclockwise, so that means the angular acceleration is clockwise. Okay, last equation, J components. I get D alpha OB. We know that now. On the right hand side we have AA plus D alpha AB, and therefore alpha AB we can solve and get D alpha OB. We just found that that's a negative sign, and then we have a minus A sub A divided by let me see here, divided by D. Let me just make sure that that looks correct. Somehow, yeah, that is correct. Okay, so what do we put in for A sub A? It's said that A is moving upward with a speed of this, but its component of acceleration is down. So down means a negative sign, and that's going to be a minus 0.1. So this becomes a minus 0.1. Keep in mind that alpha OB was a negative, so we really can't tell from this unless we actually put in the numbers. We'll just leave that for something we can do later on, and putting it in the numbers to find out what sign that it is. So in the end, in a summary, we have omega OB we saw was a 0. Omega AB was the number that we had in the K. Alpha OB is that number we found above in the K. And alpha AB is alpha ABK. So what did we do here? Well, it looks like a lot of work, and we did. A lot of algebra that's involved. But if we break it down into small parts, it doesn't seem quite so bad. Because the rule is, for mechanism like this, on velocity, write down a velocity equation for each link. Write down a velocity equation for OB, which we did here. Velocity equation for AB. Equate those. And from that we got the angular velocity for each one of the two links. When we shift over to looking at acceleration, we do the same thing. We write an acceleration equation for OB, write an acceleration equation for AB, equate the two, we get the two equations we need to find alpha OB and AB. When you get through, write these out as vectors, because that's very important in terms of telling the person evaluating your work which direction these omegas and alphas are.